Thanks for tuning in. My name's Dillon Amaya. I'm a postdoc at the University of Colorado Boulder. And today I want to talk to you, I guess, not so much about inter-basin teleconnections, but intra-basin interactions and really the influence of the North Pacific Ocean atmospheric variability on tropical Pacific climate. I want to thank the conveners for giving me the opportunity, inviting me to present in this session. I also want to thank my co-authors, Yu Kasaka, Wenyu Zhou, Yu Zhang, and my PhD advisors, Shengping Shi and Art Miller. So when thinking about the influence of North Pacific climate on the tropical Pacific, really a lot of the literature has been surrounded or focused on this Pacific meridional mode, which is a couple mode of climate variability that evolves primarily within the North Pacific subtropical ocean atmospheric climate system. There's a cousin in the South Pacific meridional mode, but I'll primarily be focusing on the North Pacific version of this. And what makes the PMM really interesting to me is that it offers an interesting variety of ways in which the climate system integrates random atmospheric variability that originates in the extratropics in a deterministic way and makes it into a teleconnection down into the deep tropics, where it can influence all sorts of things like subsurface heat anomalies within the ocean, along the equatorial strip, equatorial wind variability, SSTs along the equatorial strip, as well as precipitation within the ITCZ. And for those that are interested in the PMM just in general, I'll just plug, I have a review paper on this topic in current climate change reports if you're interested in learning more about it. But for the purposes of today's talk, really I'm going to be focusing on the influence of the North Pacific meridional mode on El Nino, on ENSO. Looking at the lag correlation between El Nino, say the Nino 3.4 index, and the PMM, in observations, you can see that the PMM is significantly correlated with ENSO, but when it leads by about 9 months with a correlation of about 0.45. So this says that the PMM is a decent predictor of El Nino conditions with about a 9 months head start. And this is interesting because the PMM peaks as a climate mode, it peaks in boreal spring, which is historically a period during the annual cycle that we typically have pretty low skill in predicting the following winter's ENSO conditions, what we call this spring predictability barrier. So if we can improve our understanding of the way PMM interacts with ENSO throughout the year, then in theory we could improve our ability to predict El Nino conditions, particularly at longer leads during the spring predictability barrier time. So that's our goal here. When people have thought about the PMM in the past, in the previous literature, most of this has been in sort of an idealized setting or in climate model simulations that have very little information about the real world. So thinking about El Ninos in a model or PMM in a model with less ties to how these PMM events interacted with real world historical ENSO events. And so what we're going to be doing in this study is looking at the importance of North Pacific SST variability on the development of historical ENSO events and quantifying the different ways that this happens in sort of a model observational hybrid framework. And the way we're going to do this is through a North Pacific SST experiment, a North Pacific SST Pacemaker experiment that we call North Pacific Ocean Global Atmosphere, or NPOGA. For those of you that are unfamiliar with the Pacemaker experiment, basically what we're doing is we're taking a coupled climate model, in this case GFDL SEAM 2.1, and we heavily restore the sea surface temperatures in a region, in this case the North Pacific, north of 15 degrees north, back to observations. Outside of this restoring region, the model is completely free to do whatever it wants. Basically what this will do is that if we do this enough times in an ensemble sense, we're able to measure the influence of, in this case, the North Pacific SST field on the rest of the climate system. And so practically what this means is that if we compare our observations directly to the model, we can get a sense of how much the real world was influenced by the observed trajectory of North Pacific SSTs. So let's say you just pick a point within our box here, our restoring region, and you compared the model in POGA to observations, you can see that the SST field is basically the same. So that says that our restoring is working and it's doing what we expect it to. Let's say you pick a point in the South Atlantic, in a region where we don't think the North Pacific is has a strong control on the SST variability there. Well, the model and the observations don't look anything alike. And that's just saying that the model is completely free to evolve and it has no bearing, it doesn't feel the observations at all, and we don't reproduce the observations there at all. So as I said, we can do this in an ensemble sense. We did 10 ensemble members of this from 1950 to 2016. And the ensemble mean of this is interpreted as North Pacific SST forcing on the real world climate system. So we're asking the question, can we reproduce ENSO in the real world, just given information about the North Pacific? Also, we ran an additional 10-member ensemble of atmosphere-only runs that we call INATMO, and you can interpret this as a world without ocean coupling. So if we can compare the results between INATMO and INPOGA, we can determine the importance of air-sea coupled interactions in driving the teleconnections from our restoring region into the freely evolving deep tropics and South Pacific, for example. So let's jump into the results here. Like I said, our goal is to see how much of the real world El Nino variability or ENSO variability can we reproduce just given information from the North Pacific. This is comparing observed Nino 3.4 with a control simulation that knows nothing about the real world. So obviously we have very low correlations, but now let's introduce our pacemaker framework. Let's restore SSTs in the North Pacific. You can see that the correlation goes up and we're able to reproduce a significant amount of observed Nino 3.4 variability throughout the historical record. Now we'll talk about individual ENSO events a little bit later, but let's just think about the variability. Again, we can look at seasonal correlations in this case in different Nino regions, Nino 3 to 4 from east to west along the equatorial strip. And you can see that we get a significant reproduction of observations between our model and the real world in boreal fall and boreal winter with peak correlations of about 0.4. And I just want to highlight this number here, this 0.4. We should never expect our simulations, these pacemaker simulations, to reproduce the world exactly, right? Because this is a relatively small hammer to the system. The North Pacific influence on the tropics is not a first order process. And the first indication of that was this lag correlation that we see in observations, right? Our goal should never have been a correlation of something like 0.1. Our goal should have been something like a correlation that we see in the real world, something like 0.45. And that's what we're getting here. We're getting correlations of about 0.4, saying that the North Pacific has about you can explain about 16% of the real world observations, given information and teleconnections coming from the North Pacific. And so there is some evidence here, right? Our IMPOGA experiments have skill at reproducing observed ENSO in boreal winter and fall. So how do we know that this skill is due to teleconnections associated with the PMM, or maybe there's other things going on? So to look at that, we're gonna look at a composite PMM event. This is the evolution of, say, the average positive PMM event in the IMPOGA coupled experiment. And it's going across a transect, a Havmuller transect that goes from the northeast subtropical Pacific down onto the date line on the equator from 0.0 to 0.6. You can see that here, 0.0 to 0.6. So this is going from the northeast to the southwest. And this is the time evolution of that average PMM event over the course of its lifetime in the coupled experiment. So there's 10 ensemble members, 17 positive PMM events. So there's 170 independent samples going into this composite. These vertical black lines show the edge of our restoring region in the model. Everything over here, this is all SST in the shading here. Everything over here is restored in the model back to observations, but everything over here in the deep tropics around 0.6 and 5, right? This is completely free to evolve. And in between is a linear buffer zone between the restoring and the freely evolved zone. So let's interpret this. We have SST anomalies. We're gonna add zonal wind anomalies. And finally, we'll add latent heat flux anomalies. So I know this is busy, but we're gonna step through it pretty carefully. The first thing to note here, this is saying the average PMM event and its evolution, average warm PMM event and its evolution throughout the historical record here. The first thing you notice is that the warmest SSTs occur in the spring, right? This is, again, the seasonal peak of a PMM event tends to be in the springtime. And the first sort of teleconnection that we might be able to discern from our restoring region down into the deep tropics occurs in this sort of time period, going from the about middle of spring down into early parts of July. You can see this southwestward propagating band of positive SST anomalies that are co-located with westerly wind anomalies and positive, in this case, downward latent heat flux anomalies. And so this is indicative of WES feedback, this wind evaporation SST feedback, which many studies have shown can drive a southwestward propagation of anomalies from the subtropics down onto the deep tropics, which in many ways gives the PMM its sort of northeast southwest pattern, just like this. So This seems to be one opportunity that our model is taking advantage of to teleconnect its signal down into the deep tropics. Once these zonal wind anomalies reach the equatorial strip, you can see that they begin to grow in magnitude, as do the SST anomalies. So we can look at what's going on the equator by looking at a zonal transect, Hofmüller transect along the equatorial strip, this transect B. That's what's shown down here. It's more of a classic zonal Hofmüller. So you can see that in July, that's when the anomalies significantly arrive on the equator and they start to grow into the fall and the winter. And you can see that as a result of these increased zonal westerlies, you kick off ocean dynamics. You kick off downwelling Kelvin waves, and you get a classic El Nino event. So this is really cool. This is saying that in our model, just by prescribing North Pacific SST anomalies, we're able to produce an ENSO event at about a 9-month lag due to a teleconnection from the subtropics down to the deep tropics associated with this WES feedback-driven propagation of SST's latent heat and zonal wind anomalies. The next sort of thing to focus on here is obviously the amplification of these anomalies, right? This is indicative of Bjerknes feedback. This is saying that the model is the equatorial ocean dynamics have been kicked off, and the anomalies are able to grow and are prescribed SSTs in the North Pacific produce downstream anomalies that are strong enough to influence deep tropical ocean atmosphere interactions. So that's really neat. And then finally, there's also this resurgence of the zonal wind field here in the summertime and early fall to late summer, early fall. And it sort of represents a secondary interaction between the subtropical North Pacific and the deep tropics. Let's think about that in a second, but first we'll compare these results to the uncoupled AGCM runs. And so comparing the wind anomalies between this panel and this panel, we'll be able to say with some certainty the importance of local air-sea interactions in driving the wind field outside of our restoring region, as opposed to just being a downstream response to having warm SSTs here, basically. So for one thing, during the springtime, you can see that the zonal wind anomalies in the restoring region are not reproduced in the uncoupled run. So this is more evidence that local air-sea interactions related to WES feedback are important in driving these wind anomalies. Whereas in the fall, you get this really strong uncoupled downwind response that extends all the way down to the equator in the fall time. So this is saying that local air-sea interactions are not important necessarily in driving some of these wind anomalies along the equatorial strip during the summer. So what's going on here? Well, we can look at the ITCZ and its climatological position. This is the shading shows the climatological position of the ITCZ, and the colored contours show its anomalies relative to this composite. And basically what you see is that in the springtime, the ITCZ is as far south as it's going to be during its seasonal cycle. So it's not particularly sensitive to these off-equatorial anomalies, SST anomalies. But in the summer, in the late summer, early fall, it migrates much further north. It's as far north as it's going to be in its seasonal cycle. And it's much more sensitive to these anomalies. And so you end up getting a northward shift in the ITCZ, which we can look at in 2D to see how that influences the large-scale atmospheric circulation. So this is the same composite of PMM, but we're just looking at late summer, early fall, August through October. And basically all I'm trying to show you here is that in this uncoupled run, you get a northward shift of the ITCZ in the late summer, just as we showed before. And as a result of that enhanced convection, enhanced heating in the mid-troposphere, you get a gill-like atmospheric response, this large-scale cyclonic circulation that extends all the way down to the equator and creates westerly anomalies along the equator that would tend to favor El Nino conditions in the following winter. So at least a portion of the downstream response to the PMM in the summertime is actually uncoupled from the local ocean, which is really interesting. And we call this thing the summer deep convection response. So looking at the equatorial zonal wind anomalies averaged along the equator and comparing them to subtropical SST anomalies here in this box, you can see that these things are correlated with each other. But the outlier I want to point out here is this 2015 event. It was the strongest PMM event on record, much stronger than anything we had seen. And what makes that really interesting is that if we look at individual El Nino events, we really don't do a great job of reproducing a number of the strongest El Nino events, except the 2015-2016 El Nino. Our model does a really nice job of capturing the overall evolution of both the failed 2014-2015 El Nino and the really extreme 2015-2016 El Nino. And this seems to be because in August through October of 2015, there was a really strong SDC summer deep convection response, in the real world associated with this large PMM event that strongly contributed to the extreme El Nino. So I'm just going to leave with some summary points here. Please feel free to contact me if you have any questions. Thanks.